In this video, we are looking at properties of the exponential function. You work with this with the GeoGebra, so hopefully this video will be a helpful recap of what you did, and maybe I'll give you a bit of vocabulary that you didn't have when you were trying to answer my questions from the worksheet. So what I did so far over here is I added a slider. It's over here. It takes values between 1 and 10, and you saw there's a function moving as I move the slider. The function is a to the power of x, so it's 1 to the power of x when a is 1, but as I move I'll get different exponential functions. We are trying to look at how they behave. So here we are looking at the graphs of exponential functions when the base is a number greater than 1. I only consider the base to be up to 10. There is nothing special about 10. I could have considered other numbers, but I guess you see what the pattern is. We start with 1, which we say we are not going to consider as one of the exponential functions, but for values very close to 1, we see how the function changes and gets more and more steep. And if we were to consider the slider to take values even bigger than 10, then the function in the first quadrant will be even steeper. So now that we saw how these functions look like, let's see if we can write down some of the properties that they have. We are in the case a greater than 1, and we are looking at the functions of the form a to the power of x. And we just saw in the picture that these functions look like something like this. So let's see some properties of these functions that are worth mentioning. First of all of these functions, they are getting bigger and bigger and bigger. So as we consider larger values of x, the value of the function is also larger. So we say that these are increasing functions. This is one of the properties we're going to mention. Another property that we should consider is that there are no x-intercepts. A to the power of x is always greater than 0, so it's never equal to 0. But for y-intercept, that's easy to find. We want to see what is the value of y when x is equal to 0, and that does not depend on a, because a to the power of 0 for a greater than 1 is equal to 1. So the y-intercept we see over here is at the point 0, 1. What else can we say? We can see, and maybe we should add it over here in the point 2, we can see that when we consider values of x that are very, very small, we say x approaches minus infinity. In the picture, we are talking about what's happening over here. We see that when x approaches minus infinity, then the value of the function is approaching 0. So we never touch the value 0, but we get really close, as you can see inside the pink area. This is what we call a horizontal asymptote. Horizontal, let me write the whole word because it's a new one. Asymptote. What this means is that, this is horizontal, and this is a value that the function gets close even though it's not touching. So the horizontal asymptote is y equals 0, is the horizontal line y equals 0, and this happens as x approaches negative infinity. I know this approaching an infinity and asymptotes is they're all new concepts for us, but well, you're going to start knowing a little bit about them, and then next year you're going to be much more familiar with these concepts. Again, talking about what's happening for very far away values of x. So what's happening when x is huge? So we write x approaches infinity. we mean positive infinity. So what happens when our value of x is 1,000 and a million or million of millions? So now we are talking about what's happening in this part of the function over here. So what happens to the function as the values of x increase and increase? And what we can see from the picture is that the values of y also increase and increase. So we write that y approaches also positive infinity. What else can we say? Something that was mentioned in class. When we consider the value of x1, then we know that the value that the function takes over here, this point over here, it has coordinates. Let me write it here. It's going to be 1 and a to the power of 1. So it's going to be 1a. So 1a is a point of the graph of the function. It's a point of the graph. And why is this important? Well, let's say we want to very quickly sketch the graphs of two functions. Y equals 2 to the power of x, and different color, y equals 7 to the power of x. So small picture over here. We know the shape they have. We know the y-intercept. We know what happens towards minus infinity, what happens toward plus infinity, something like that. But how do you know which one is the one that corresponds to 2, and how do we know which one corresponds to 7? They have the same shape, but how can we distinguish them? Well, let me fix this a little bit. This wasn't very good. We use this auxiliary point that I mentioned over here. We know that, let's say this is the point 1, and then this is the point 1 in the, sorry, I don't want the point 1. I want here to mark where is the point 2 in the y-axis, and where is the point 7? So 2, 4, 6, let's extend this a little bit. Here is 7. So now we have 2 points for those functions. So for y equals 2 to the power of x, we know how it looks. We know, I did this wrong. Let me go back. We know the y-intercept at the point 1. Let me go over here, and then we know 1 point, so we know more or less how it grows. On the other hand, if we want to draw y equals 7 to the power of x, then it's going to be more flat in the negative side, and then it's going to grow faster in the positive side. So this point is useful if we need to compare 2 or more of these exponential functions. Now I'm back in GeoGebra to look at the functions a to the power of x when we are considering values of a that go between 0 and 1. So I changed the settings of my slider to go between 0 and 1. Here I'm at 1. We know at 1 we are just in the horizontal line y equals 1. But then as I move it, we see how in the second quadrant the function is getting more and more and more and more steep. And well, for 0, the software is just drawing the function as a constant 0 in the positive axis. But we don't care about 0. We want values that are strictly bigger than 0, between 0 and 1. So for instance, over there, let me move a little more so we see what's happening. So what are the properties of this function is what we want to look at now. Now we are looking at values of a that are between 0 and 1. Again, y equals a to the power of x. And again, I'm going to do a quick picture over here. We only care about what's happening in the first and the second quadrant. And the function, as we just saw, looks like something like this. So let's see, what do we know? I kept over here what are the properties for the case a greater than 0, so we can compare and contrast. In the case, sorry, I should have said a greater than 1. In the case a greater than 1, we had that the function was increasing. Now the function is decreasing, so it's getting smaller and smaller. For the x-intercepts, again, we have no x-intercepts. No x-intercepts. The a to the x is always greater than 0. But over here we can see that When x gets really huge, so we say x approaches infinity, then we can see the behavior of the function over here. I'm looking at what's happening here. The branch of the function on that side is getting closer and closer and closer to the y-axis. So we say that y approaches 0. And again, we say that there is a horizontal asymptote. Y equals 0, but this time is as x is approaching plus infinity. So that's slightly different than the previous case. For the y-intercept, this is, again, we need to find what is the value of the function at 0. Is a to the 0, so it's 1. So again, the y-intercept is over here, is the point 0, 1. Now we already know what happens when x is huge. Now what about when x is very small? So what happens to the function when x is approaching negative infinity? So we are looking at what's happening over here. And what we see from our picture is that the value of the function is getting huge and positive. So we write y approaches infinity. So similar to the other case, we have kind of a mirror behavior. This time is when x approaches negative infinity. Again, let's look at what happens when we look at, this time when we look at the point -1, a to the power of -1. This is a point on the graph. And let's see if we need to compare two such functions. I don't know, let's say we are looking at y equals 1 over 10 to the power of x and y equals, I don't know, 1 over 3 to the power of x. Let's put brackets to make this more clear. And yeah, we can use a different color for this one over here. And we want to graph those functions, and we know that how they look more or less. We just need to know which one is the one that is more steep and which one is the one that is less steep. But then we can look at what is the value of 1 over 10 to the -1. That's 10 to the 1. So this is the value 10. So the one that I'm drawing over here more steep is the one that has base 1 over 10. When I have base 1 over 3, when I find the 1 over 3 to the -1, so the image of the value -1, I get 3. So this function is going to be not that steep. So again, this point could be useful if you are trying to compare two functions that look similar, but the base is slightly different.